Lonlege, please join me on the stage. This is your pointer. Yeah, your turn.
I love that. Testing. Let me know if you can hear me. Perfect. Hello, everyone. How's everyone feeling? My name is Sean, and I actually used to be a core dev at Parity. Worked on our Rust Ethereum client back in the day. Rust, or it was Parity Ethereum. Also worked on Substrate, POLKADOT. No longer at Parity, but still actively contributing to the ecosystem. I recently made a fellowship member, for those of us who are familiar with the Polkadot Fellowship. And today I just want to talk a little bit about Polkadot interoperability, how that relates to scalability, and sort of the ways in which we can make interoperability today in the ecosystem much better, much more ergonomic, much easier to reason about. So let's just dive into it. So maybe we should take a step back. Why interoperability? What did Gavin would see that made him sort of take the fork in the road and go start off Polkadot? Well, start with some facts. Synchronous application composability is just unsustainable, right? You have a single blockchain network. It has nodes on this network. And they're all just basically re-executing what is the same set of blocks. At some point, you run into this issue where a single application can sort of starve out all of the other applications on this network. Conventionally, we refer to this as thread starvation. But that's bad, right? This is bad for scalability. Also because this drives up the costs for block space, as well as having these multiple applications compete for block space. Some of them might not be able to afford this block space. Like, I just want to transfer some fees. I just want to transfer some funds. NFT mints, they're willing to pay thousands of dollars to mint their NFT. I don't really want to pay $1,000 to transfer $10. That doesn't really make any sense. So Gav says, okay, what if we had multiple blockchains that were specifically tailored to different applications? Now, they don't have to compete for block space. And as a result, you have cheaper transaction fees. You have higher transaction throughput because they're not competing, obviously. And there's more flexibility for app developers because you can now tailor your blockchain at the base layer to be highly performant for your application-specific purposes. And of course, this is kind of a side effect. This introduces a much more sustainable tokenomic model, whereas if you had some DApp, your users essentially have to pay rent to the base layer. And then what's the sustainability of your token model? It doesn't really make sense. But in this new case where the token actually powers the blockchain that your app lives on, then of course you have a much better sustainable model. Okay, maybe it's not all good, this new idea of making everything sort of sharded on its own blockchain. Of course, this introduces the need for asynchronous composition. So applications cannot immediately call another application for some data in the same block. They kind of have to wait for multiple blocks. And you might think that this is bad. I don't think it is, actually. I don't think that it is. And the reason for this is because, actually, let's take a step back into traditional software systems. You have some software, it runs perfectly well on the single-thread model. You want to scale it up. Of course, you want to add more threads. You want to add more machines. At that point, your process can no longer be synchronous, right? It has to become asynchronous. Actually, you could still hold on to your synchronicity for dear life and try to do mutexes and try to do these locking semantics. Of course, you quickly run into deadlocks and all kinds of other issues that these locking primitives for synchronous communication between threads introduce. And after a while, you become enlightened and realize, okay, maybe I should be doing lock-free primitives like channels, like the actor model, where instead threads just pass messages to each other, telling them what they're doing, and sort of handing off work to another thread, right? So interoperability, if we come back to the Web3 model, is this lock-free message passing for distributed state machines, right? And the ability to do this actually is what unlocks true scalability, right? You can have a single-threaded process and try to maximize how many transactions can fit into that process, into this state machine. But ultimately, you can't beat someone else who can add more state machines to their process, right? The same way you can't beat a multi-threaded process if you're just a single-threaded process. So it's kind of a fun meme. I think that people who are looking for blockchain scalability will eventually realize that they're asking the wrong question, and it's not the answer is not to throw more machines to it. It's not to try to like ZK prove everything, and of course that just leads to centralization. It's really just to add more logical cores to your process. So this is where we start to see, okay, Polkadot actually is leading this interoperability revolution, as it were. Polkadot itself has sort of multiple processes on the relay chain: staking, balance transfers, governance, what have you. And slowly, they are bringing these processes down to what are called system chains. We've already seen a few launched: the Asset Hub. We've seen the collectives. There's also Bridge Hub, which will handle bridges to other ecosystems. But there are more planned. In fact, the idea would be that the relay chain does nothing but just validate parachain blocks. And if you wanted to do, for instance, staking, you wanted to do core management for what is this new core time paradigm that Gav unveiled for his Polkadot version 2.0 model, that will all happen on the parachain level, right? And all of these processes would communicate asynchronously with each other. You can move your assets from the Asset Hub into the staking hub, where you can stake and you can unstake or what have you. But all of this is good and all, but there are still some issues with cross-chain messaging. For instance, how do you guarantee that this remote process or this remote application that you're messaging is executing your messages correctly? The only solution to this would be to obtain some sort of execution proofs, you might say validity proofs. But actually, in Polkadot, we don't need these sort of cryptographic validity proofs, right? The relay chain itself can enforce the execution of messages. And this is what Gav referred to as accords, where essentially parachains will share some code, and the relay chain verifies that this shared code, is being executed correctly. So personally, I don't really like the name relay chain. I think it's an artifact of HRMP, which used the relay chain as a message relay chain. I think Polkadot itself is more of a bridge network in that it facilitates blockchains to communicate with each other, and that's really what it does. And it does so by validating their state transition functions. Okay, I already touched a bit about HRMP, and it's this protocol that uses the relay chain as a transport layer for messages. So parachains, they push messages up to the relay chain, and the relay chain will push messages down to the destination parachain. Fortunately, it's not very scalable. As you can imagine, for instance, if every parachain is pushing messages up to the relay chain, then the relay chain forms what is this bottleneck in parachain messaging. And of course, there's all sorts of issues, in fact. And even with all of the complexity of HRMP, it still lacks the ability to read relay chain state, for instance. You can't even read your sibling parachain state. All you can do is just messaging. And so it calls into question the need for a new, more simpler protocol for interoperability. And that's actually what I would like to introduce here today. But of course, another meme just for the vibes, for the parachain developers with us here who are familiar with XCM and sort of the verbosity of XCM. And you just wanted to transfer assets, have to now deal with this verbosity. But the thing is, this verbosity has been seen before in the developer landscape, right? If you remember XML HTTP request, which was the first API that the browser gave to the general execution environment as to how you could make HTTP requests. A lot of people did not like this. It was a bit too complex. Actually, it was very powerful, right? Because you actually could hook into the literal transport protocol behind it, right? They thought people would want to do all this stuff, but really people didn't care. People just wanted to send messages and receive responses. And so this is, just sort of a meme to show you that we've seen this sort of thing before, and eventually this verbosity made way for more simpler interfaces, like Fetch, Ajax, or Axios. And so, like I said, XCM will have to make way for something more simpler that developers can reason about easily. So this is where the sort of interoperable state machine protocol comes in. This is something that we've been looking into since the beginning of the year, sort of asking ourselves, how can we model cross-chain communication in such a way that's easy to reason about, familiar to developers, and doesn't introduce any new cognitive overhead. So we've modeled it after HTTP, actually. So you can imagine you're just doing HTTP requests in a blockchain. Fundamentally, it only allows you to do two things and two things only. Post requests, which is for sending messages, arbitrary messages. We don't actually enforce a messaging format, so you can really put whatever you want into what are these requests. You can put JSON. You could actually also put an XCM message. We don't care. All that matters, though, is that the destination chain or destination module knows how to interpret this message, kind of like how it already exists today in Web 2. You post some data to a remote server, and if the server cannot interpret your message, you get an internal server error. This is how it works. So the same thing should happen in the blockchain space. So this research and development, we're lucky to be funded by the Web3 Foundation, and it currently supports parachains today, as well as solo chains. Actually, this solo chain interoperability is powered by our Grandpa Light client. So we have an implementation of the Grandpa consensus protocol. So solo chains can also use ISMP to talk to parachains. But even better, because we have this Grandpa Light client, the Polkadot relay chain and the Kusama relay chain can also interoperate over ISMP. So this is a very, very top-down integration protocol. We already have support for pallets, as modules, as well as the EVM contracts. We're already investigating what it will take to support Ink and, of course, the Ethereum blockchain as well in this protocol, as well as its rollups. And like I said, really what you can do with ISMP is you can make these GET requests. And we're already seeing teams thinking about what this GET request truly means. For instance, Akala will be able to use this to mint what are derivatives of your stake on the relay chain. And even if that moves to a parachain, they can still read a parachain state. For instance, Invarch, who builds DAO tools, are already thinking about how they can use this to implement what is this bribe protocol, where you can essentially read the proposals from the relay chain and then make them available for people to bid on how a pool of funds should vote for these proposals. For instance, we're also seeing multi-asset transaction fee collection for any parachain, using the price data on DEXs in the ecosystem. For instance, Hydra DX is a decentralized DEX, and they can basically be this oracle for price data. As well as Kilts as well, they have this decentralized identity that is on a parachain, but how can you read this information from any chain, really? This is powerful for applications that want to leverage Kilt's decentralized identity system. Of course, we have post requests, which, like I said, allows you to just post arbitrary data to a different blockchain. And the only thing I would say that a developer needs to think about is timeouts. So say you send out some requests and you don't get a response for it, you basically get a timeout. And this is not that very complicated, right? It's similar to what you get in HTTP. If you send out a request, you either get a response, you get an error, or you get a request timeout. And so you just have to handle this however you see fit. So this is also another meme about how I see the sort of landscape of interoperability today. We've already seen something that works really well. Somehow, no one else has tried to replicate this in the blockchain space. Instead, what we've gotten are these very complicated protocols that are trying to do multi-hop routing, trying to do relay incentivization, trying to do four-way handshakes, whereas the answer was in our faces all along. So I'll touch a little bit about, again, what Spree does and why it's needed specifically. So in the parachain model, in the parachain runtime, there's a call that actually allows you to overwrite arbitrary parts of your state, right? Applications have their own state, but there is this frame system that can just write to any part of the state. It needs root, but if a parachain doesn't have sudo removed, or maybe it's actually not super active and no one's really looking at what governance referenda are being passed, then really a parachain could convince, or parachain A could convince parachain B to mint some infinite amount of funds through just cross-chain messaging, because in the happy path, some funds had to have been burnt before the message gets sent out to, hey, mint these funds. But in this case, parachain A could just write that message directly over, like sort of sidestepping the module that handles this messaging. And that's pretty dangerous, in fact. So this is where we introduce Spree, and so we separate out cross-chain modules themselves into having their own state tree, and the relay chain sort of enforces that these modules are being executed correctly. In fact, if you have a Spree module and you have your conventional runtime modules, they cannot interact. The only thing that can modify your Spree module's state are Spree transactions. So this brings back this trust-free cross-chain messaging that we so desire. And of course, if you wanted to change your Spree module, actually all of the parachains would have to vote on their chains, of course, if they had the governance module, to sort of change this module. And it would have to be a passing vote for all parachains. No single parachain can change the Spree module. So, giving all of these tools, it's clear that Polkadot will be this sort of primordial soup. And this is a reference from abiogenesis, the conditions for life 4 billion years ago. Polkadot will have these conditions to spawn the most advanced cross-chain applications, the most scalable cross-chain applications, just because of the tools that parachain developers have at their disposal: ISMP, Spree, XCM. And we're very excited about this. But one thing that I want to sort of bring to top of mind is that these tools don't just enable cross-chain communication, but if you go back to the beginning of my talk, they also enable this multi-core sort of standard for applications, right? So if you think about it, just by having cross-chain communication, you can also use that as a sort of synchronization primitive between multiple instances of your application across different parachain slots or parachain cores. So yeah, what is multi-core parachains actually? I think Gav already described Polkadot as a multi-core computer. And so if you wanted to really make use of all of the resources that Polkadot provides, then it makes sense for you to launch what is a multi-core parachain. So a parachain that uses multiple cores. But then how do you synchronize the load, the sort of work that each parachain core is doing? You need cross-chain communication, right? And so this is where cross-chain communication starts to show itself as a scalability primitive. And so, for instance, you could use ISMP to sort of orchestrate multiple worker cores, and you have a master core that just sends work out to these parachain cores. Or you could do long-running computation on one core and read the results of that computation from another more user-facing, lighter-weight core. This is still cross-chain communication, but this is now sort of scalability in play. And like I said, with these primitives, parachains can scale beyond what is possible really in any other ecosystem today. And so that's the end of my talk. I just want to leave you with this meme so that we can all start to be these synchronizers of distributed state machines beyond just threads. Thank you.
Thank you, Sean. It was brilliant. Perfect. I hope you guys better